Good afternoon, all. Welcome back to the second part of the session before noon. We are continuing with the topic on biomaterials and prosthetics, theory and case studies. Professor Mukesh, sir.
Yes, yeah.
You're welcome, sir.
Morning we looked at polymers because polymers have tremendous advantages. Although metals have advantage with respect to their strength, mechanical strength, especially for load-bearing applications, polymers have advantages with respect to tailor making of properties, modifying the surfaces, making the surface biocompatible, reducing biofilm formation. So polymers have that sort of advantages, and we can use different polymers for different locations in the body, for different durations, modify the surfaces, and so on. So, and also I mentioned about composites. That's opening up a new area where inorganic material could be combined with the polymers to achieve enhanced properties, enhanced mechanical, chemical, inert properties, which a normal polymer might not have. So polymers have big business, but of course they also have little bit disadvantages, like the monomers could be toxic as well. Okay. Main advantage of metals is they have good load bearing capacity, especially if you are standing or if you are lifting something with your arms. Only metals can be used. As of now, polymers cannot be used, although polycarbonate is one polymer which has very high mechanical strength, which is comparable to some metals as such. But one of the big disadvantage of metals is they are non-biodegradable. That means they remain in the body forever unless you remove it, conduct another operation and remove it. So if somebody is having a orthopedic issue, a fracture, for example, they put in bone plates. It could be stainless steel or titanium. So it remains in the body forever until the bone grows fully. It may become difficult to remove that bone plate because it might be fully embedded with the bone. So the surgery might be more tricky or dangerous. So the plate remains inside forever. So many people with the fractures may end up having stainless steel or titanium remain in the body. And if you are talking about knee replacement, you are going to have cobalt, chromium remaining in the body. But the metals have many advantages, especially from the technology developed in space and ammunitions. Many products came into biomaterials as well, with the enhanced property, with the enhanced biocompatibility, shape, memory, alloys, and so on. So metals have many properties, but the main problem is they are not biodegradable. They remain in the body. So we started looking at a metal called magnesium, which is bioresorbed. And as you know, magnesium is a part of the human system. So it has good bioacceptability as well, actually. So we did some work on magnesium. So that's what I'm going to talk about. This work was done in collaboration with Dr. Gopalan, who is an orthopedic surgeon from Christian Medical Center, CMC, Vellore. So bone is extremely important. It's a dynamic form, connective tissues. It continuously remodels throughout the life. That means it changes its shape and even size as a function of time as we go along. Of course, it's needed for the locomotion, load bearing. The entire body is held by the bones in the leg. It protects the internal organs as well. All your heart, lungs, they're all inside. Okay, and then it's a storage place for calcium, phosphorus. These are very important ions. Hemostasis, because it maintains the system properties constant at any adverse external environment. So that way bone is very important. But the bone fractures due to trauma is huge. If you look at USA data alone, 1.3 million procedures occur. Trauma, accidents, cancer, and other diseases. And so globally, it's a very big issue, and the medical costs for these type of repairs, we are talking in terms of 215 billion US dollars. That's a big amount actually. Okay, and it can keep increasing rather, because as the age population increases, especially if you look at Japan or even many Western countries, the average age of the person keeps increasing. So falls can lead to these type of fractures. So this number can keep going up only. It will not be going down. In fact, it will be going up and up actually. And also the developing countries who want to have better quality of life are also looking at better treatment strategies, especially for orthopedic related issues. Actually. Okay, so these type of issues will keep going up. So let's look at long bone segmental. We looked at long bone. So what is long bone? Okay, these are bones like tibia, femur, for example, fibula, radius, ulna, humerus. These are bones which are almost 1 foot in length. You know, these are called long bones. So here the defect can happen. A part of it is broken because of some accidents or because of some other injury or health related and so on. Okay, and especially these defect are of about 5 centimeters or more. They are called critical segmental defect. If the defects are smaller in length, that means 1 inch, or that is 1 inch is 2.5 centimeters. So 2 centimeters or 3 centimeters, the bone starts growing. So they put in a plate as the bone starts growing. But if we are talking about 5 centimeters or longer defect, bones will not grow on its own. So it needs a lot of support for it to grow. They are called segmental bone defect, critical segmental defect, which are greater than 5 centimeters. So body cannot heal it on its own. So it needs more specialized reconstruction. Okay, so this we are talking about these long bones which are longer in size, more than 1.25 foot long, like the one in your thighs and legs and arms and hand and so on. Actually, so this can happen because of high energy trauma, that is big accidents, tumor related, osteomyelitis. That means infection to the bone. So bone gets infected and then large portion gets eaten away. So in order to prevent or stop the infection, what they do is they cut the bone on either side of the infection sufficiently long and remove that. So there is a big gap produced. And if it is more than 5 centimeters, they call it critical segmental bone defect. Blast injuries, revision surgery, modifications to existing. So people who have, say, bent knees, so they want to modify their legs by cutting some portion of the bed, leg, and so on. Actually, that's called revision surgery. So generally, stainless steel 316L is used for as bone plate. L means it can it has less corrosion. That means it has better corrosive resistance, unlike stainless steel 316. So as you can see, there are a lot of holes in that. So these are used for placing screws, and so the plates are placed and it's screwed on the top and the bottom with different screws actually. So these are called stainless steel 316L bone plates. These are cheaper, but they can still corrode. Although 316L is less corrosive when compared to 316, and that also corrodes. So came titanium bone plates. On the right hand side, you can see the picture. Titanium does not corrode. Okay, so that way titanium is quite good. It's got inert properties. But titanium also has a lot of disadvantages, including bacterial adhesion. We talked in the morning, biofilm formation and so on. But the main advantage is it does not corrode, unlike 316. But titanium is more expensive. In India, quite a lot of stainless steel is still being used. Titanium is also slowly getting used now. And those who have even problems like diabetes, if they have a stainless steel bone plates, in the long run, it may start giving problems actually. So the Bottom pictures, you can see some X-ray pictures of how these bone plates are placed. So we have injury to the bones, top and bottom. They are placed, and these plates are placed, and you can see the screws at the bottom right hand side picture. Okay, the screws are placed and screwed onto the bone, and small, if the defect is very small in length, slowly the bone starts remodeling and growing, and they get connected, but the bone plate may remain inside. So removing that is a bit long process. So sometimes, generally, it is left intact inside. Okay. How do you address long bone segmental defect? There are many techniques that are being practiced as of now to address long bone segmental defect. The first technique is called vascularized fibular grafting. Okay. The second one is called distraction osteogenesis with an external fixture. So they have an external fixture with screws, and they will keep pulling it slowly. Few weeks, little bit pulling, few weeks, little bit pulling, and so on. So the bones inside slowly get pulled. It's very painful, and over a period of several months, the slowly bone starts getting pulled and starts growing and coming. Okay, so this is used. This is an external fixator. The third one is intramedullar nailing. So they have a long nail which is placed inside from the top portion of the bone to the bottom portion. Okay, so as you can see in the X-ray picture, and the bone will start growing as such. But in these techniques, the patient cannot use their feet. For example, if it is a long bone segmental defect in the foot region or in the thigh region, because it still cannot take in the weight of the body. So then came the cylindrical mesh technique. Okay, so you have a cylindrical mesh of titanium. Currently, titanium is being used here, as you can see here. So it is placed in between these gaps. Like I said, long bone segmental defect is more than 5 centimeters. So you can have titanium mesh cage about 5 centimeter long placed in between. So with the intramedullary ring, so quickly the patient can start using the leg, for example, and the load bearing also improves. So this is currently being practiced because quickly the person can get back into their feet, unlike the other three techniques which is talked about. So titanium, this is approved by US FDA, Food and Drug Administration. So it came into in 2000. Okay, used for long bone segmental defects. So it's hollow, okay, mesh cage like, called fenestrated nature. So immediately the limb gets stabilized, so the person can start using the leg, for example, and it improves the weight bearing capacity. So this is some, you can see some radiograph picture after 1 year, fresh one here, and after 1 year, immediately it starts improving. So typically how titanium is used here, so we have the initially pre-operative radiograph. Okay. So they take the allograft. Allograft means it's some part of their bone, some other part of the bone, crumble it, crush it nicely, and fill this titanium with that. Because it's allograft, it will improve the contact, and it will be more biocompatible. And then it is placed in between these gaps, as you can see here, lateral view. So this is how titanium is being used. But the point is, titanium is not biodegradable, so it will remain inside the body and in that place forever and ever, even if the bone starts growing. But the main advantage is quickly it heals. Person can start using their limb, putting down their weight. So this titanium mesh cage will be filled with their allograft of the person who is. Problems with titanium. Many problems are there because titanium has high modulus. As you can see, the tensile strength of titanium is 345 megapascals. as against cortical bone, which is 50 to 150 megapascals. Again, compressive strength of titanium can be 250 to 600 megapascals. Okay. Whereas compressive strength for bone is 100 to 230. Elastic modulus for bone is 7 to 30. Titanium is 102. Fracture toughness 2 to 12. Titanium 58 to 67. So titanium has very high modulus when compared to bone. So there is something called stress shielding that can happen. What is stress shielding? So if you have some part of the load-bearing region with titanium, which has a very high modulus when compared to the bone. So most of the load of the person will be transmitted through the titanium. So less load will be transmitted through the bone. So the bone over a long period of time will get porous. So this is a very serious problem with metallic implants in load-bearing areas, because these will become slowly porous in nature. That is why there is a lot of research being done to bring in metals which are in strength, tensile strength and elastic modulus closer to the bone. Still, success has not been achieved, but people are looking at alloys, putting in aluminium, zinc, vanadium, so many different metals, so that these mechanical properties could be brought down and down. So ultimately, if you have a metal which has properties similar to the bone, then the stress shielding issues are not there. So if somebody has a titanium rod placed in the leg, and if he or she walks, most of the load will be transmitted through the titanium. The load through the bone is less transmitted, so it slowly does not function properly. It loses its strength, it becomes more porous, so those portions get weakened actually. So that's called stress shielding. So metals and metal alloys are being designed to slowly reach that of the bone actually. Titanium is not biodegradable, so it's going to be remaining inside forever and ever. Another issue with titanium, although titanium is extremely good biocompatible, bacterial adhesion is a serious problem. So that means, which I talked about before, biofilm formation, bacterial adhesion is a serious problem which could lead to a lot of infection happening. So many surface modifications of titanium is being looked at, but still bacterial adhesion is a serious issue with titanium. Okay. So these are some problems with titanium. And this is an interesting picture. If you look here, the x-axis is Young's modulus and y-axis is fracture toughness. The topmost is nickel, chromium, stainless steel, titanium. So those metals are all top. Whereas if you look at the bones, Young's modulus and all very, very low. Okay, cancellous bone, high density, low density, eggshell, hydroxapatite. Okay, is very low. The problem, hydroxapatite is very good because it's almost like bone, but the problem is we cannot shape it into different shapes. Silica is another material. There can be hydroxapatite, silica can be used as a filler, but not as a material shaped properly. Cortical bones, biosilica, that is bioglass, they call it, almost silicon dioxide, zirconia, as you can see, still it's got high Young's modulus, okay. Silver. So the goal is to design new materials, new alloys, so that its values keep coming down and down, almost coming to that of the bones actually. Many inorganic materials have such low values, but the problem with the inorganic material is they have extremely poor tensile strength, and they cannot be shaped into different shapes as desired, and all these are issues. They cannot be surface modified, unlike polymers or metals. So these are some issues actually with the inorganic material. Most commonly used material for bone scaffold. Okay, so bioceramic, like I said, hydroxapatite, tricalcium phosphate. So these are used as fillers if there is an infection or if there is a cancerous growth. So they remove that part of the bone, so there will be hollow regions created. They may fill it up with tricalcium phosphate. Bioglass is a silica type. Hydroxapatite is used quite a lot, but it cannot be used per se as such. Then we have biopolymers. We have natural polymers, that is biopolymers like collagen, gelatin, silk, chitosan. But the problem with this is getting large quantities of biopolymers is a big issue. How do I get tons and tons of silk, for example? So that's a problem. Whereas synthetic polymers like PLA, PLGA, PCL, all these are also used, coating of different material with PLGA, PCL, and so on. Then biocomposites are also used, L-lactic acid and hydroxyapatite, tricalcium phosphate, polycaprolactone, tricalcium phosphate. So these sort of composites, advantage of it is when you use inorganic, most of the inorganics are very biocompatible, like tricalcium phosphate, hydroxyapatite, bioglass. They're all very biocompatible, and polymers can be the base material or the parent material. So together, you get a lot of properties. Of course, load bearing is much lower, but with polymer in present, load bearing can be improved. So these composites are also used quite a lot in biomaterials for bone scaffolds, bone implants, fillers, and so on actually. So you can think of coating metals like stainless steel or titanium with these type of composites, because as you know, hydroxyapatite, tricalcium phosphates are very biocompatible, almost like your bone. And you could have polymers which are biodegradable, which is also biocompatible. They allow cell adhesion. We can have drug encapsulated with the polymer so that the antibiotic could be acting against the bacteria, or we can have growth factors incorporated into the biodegradable polymer. So the growth factor could enhance addition of the scaffold with the host cells. So we could think of designing different types of material for different applications. If you're looking at biofilm prevention, antibiotic could be there. If you're looking at growth factors or anti-inflammatory molecules, we can think of them, and so on actually. Polymers, of course, have problem. We talked a little bit previous with the examples. Natural polymers, they have immunogenicity. Okay, processing conditions, you need to have a big processing conditions to improve them. Poor mechanical properties. Generally, natural polymers are not used alone. If you take chitosan, for example, it has to be combined with some other polymer. Poor cellular adhesion, for example, chitosan. Poor mechanical properties. Synthetic polymers, hydrophobic, synthesized in large quantities. Many of them are approved by FDA. PLA, PLGA, PCL, they are approved. Chitosan, natural polymer, is approved by FDA. Silk is approved by FDA. And synthetic polymers, the problem is when it degrades, the degradation products could be causing toxicity issues and inflammatory issues. For example, lactic acid from PLA or acrylic acid from PMMA could be toxic and causing some problems. Implant failure. Okay, the implants after some time can fail. Like I mentioned, the early failure is mostly related to biofilm, and the later failure is related to immunogenicity and biocompatibility issues actually. So we looked at nanostructured biomaterials because the advantage of nanostructured is it can mimic extracellular matrix, number one. It can regulate cellular response, including attachment, proliferation, differentiation, matrix deposition, because the cells have to attach, then they have to proliferate, they have to differentiate, and then the matrix also should get deposited. That means if you have the collagen, okay, they have to deposit. They can also serve as a temporary 3D substrate to guide new tissue formation. So that's the advantage we have. In tissue engineering, we need high porosity. So nanostructured material can help in getting high porosity. That means it can have per gram of material high surface area. And we can also design adequate pore size. So you don't have to go very nano in size, like 2-digit nanometer scale, but you can think of 3-digit nano, like 400, even 500 nanometer, so that we can help in cell adhesion. Okay, So because when you talk about biomaterial, especially for tissue engineering, the cells, the scaffold, the signaling molecules, all we need to consider if it is going to have a regeneration properties actually. So like I mentioned, titanium has very high Young's modulus, high yield strength. So we looked at a magnesium based material, magnesium alloy contain AZ31. This is a magnesium with the aluminum 3% and 1% zinc in weight. Okay. Look at this, Young's modulus is 45, although it's not in bone, but it's much lower than titanium. Okay, it's slowly coming towards bone. Yield strength is 220 when compared to titanium, which is 345. So it's coming. So there is nowadays a lot of interest in magnesium-based alloys, because magnesium has good properties and more towards bone when compared to stainless steel or titanium, which have mechanical properties far away from bone. Number one. Number two, magnesium can slowly get bio-resorbed. That means it can slowly degrade and disappear. Number three, magnesium is part of the human system, so it will not cause any toxicity or any adverse reaction. So there is now a lot of interest on magnesium-based alloys. So that means they add different materials. Like in this example, where we worked on, we looked on AZ31, which is a aluminum zinc-based magnesium product actually. Okay. And another interesting point is zinc itself has a little bit antibacterial property. Okay, so it can also add a little bit as an antibacterial material. Okay. Okay, so we looked at AZ31 magnesium alloy, which is biocompatible, biodegradable, mechanical properties much less than titanium and aluminum and stainless steel, closer to the bone. It can degrade after tissue regeneration. So finally, you are not going to have the metal inside, unlike like titanium or stainless steel. Then the one problem with magnesium is it can degrade very fast. So what we did was we coated the magnesium surface with polycaprolactone. It's a FDA approved polymer. It doesn't biodegrade fast, unlike unlike polylactic acid or polyglycolic acid and so on. But it slowly degrades over a much longer period actually. And then it's combined generally with a lot of studies have been there with hydroxyapatite, polycaprolactone combination. And as you know, hydroxyapatite is present in large amount of the bone and also in teeth. So it's part of the human system actually. So many studies have been done with hydroxyapatite combination with PCl. So we wanted to reduce the degradation of magnesium. So we because we want to extend the life of the scaffold inside so that bone grows enough. So we reduce the degradation of magnesium by coating the surface with this polycaprolactone hydroxyapatite system. Okay. So main problem with magnesium is it can bioresorb very fast. Okay. So we created that sort of designs, and we tested it for orthopedic the long bone segmental defect study actually. We also used a polymer called pluronic F127. It's a non-toxic, biocompatible, biodegradable copolymer. It's approved by FDA. It's improved cell adhesion, collagen formation, and angiogenesis also. So we use that in combination with that. And this is almost like a surface active agent. Okay, so we worked on designing magnesium cages for long bone segmental defect application, just like the titanium mesh cage. So we took magnesium rods, and then we made that into tubes, as you can see in this picture, and then we created this sort of a cage design. Holes were drilled into that. So we ended up with the AZ31 magnesium cages. Okay, so so we got from the ingots, we made the tubes, and then we created the cage, and then we electrospun polycaprolactone with hydroxyapatite and fluoronic acid. The idea is, number one, reduce the biodegradation of magnesium. Number one. Number two, improve the biocompatibility, because hydroxyapatite is part of the bone, so it will improve the adhesion of the cells and biocompatibility. Okay, that is how this particular thing is done. So this surface treated electrospan was used for long bone segmental studies. We did studies on in vitro in the lab as well as in rabbit models to see whether they are able to heal the segmental defect in rabbits actually. Okay. So the polycaprolactone, hydroxyapatite and fluoronic acid were first coated on the magnesium cages, and then again they were electrospun on the magnesium cages. So what will be the advantage of this? You can see the uncoated AZ31 cage, and the other one is a nanocomposite coated AZ31 with electrospun polycaprolactone, hydroxyapatite and fluoronic. So provides flexibility to the reconstructed bone. Okay, avoid stress shielding because titanium and its alloys have much lower tensile strength than titanium. Sorry, the magnesium and alloys have lower tensile strength when compared to titanium. So we don't have to remove. And magnesium, as I've been telling, is bioresorbable. So in the long run, as the bone starts healing and growing, the magnesium will completely get resorbed. Bioactivity and biocompatibility are improved because we have the polycaprolactone HCA. And again, it's we are mimicking the ECM extracellular matrix, so we call it biomimetic. By having different amount of these PCL HCA coating, we can control the degradation of the magnesium. We can either slow down the degradation or we can speed it up by designing the thickness of the layer of the coating of PCL. Okay, so if you want a 6 months disappearance, or if you are looking at 1 year, 1.5 years, and so on, actually, that's the advantage. These are some scanning electron pictures of the PCL coated surfaces actually. Different amount of PCL, different amount of hydroxyapatite we did because our goal is to optimize the amount of HA so that we get uniform sized electrospun fibers. As you can see here, we got some beautiful fibers here actually. Fiber diameter around 700 to 500 and so on actually. As I mentioned, we don't want to go into very low nanoscale. For cell proliferation, we need to reach very reasonably higher nanometer scale. So we were trying to go up to almost 700, that is 0.7 micron level. And then we are looking at the biomineralization, resorption of the product. Different products which we have different amounts of hydroxyapatite, 10%, 20%, 30%, as you can see in this data. And then this is without hydroxyapatite, just the polycaprolactone alone. And this is uncoated on the top. So this is 7 days weight loss, and this is 28 days weight loss. So you can see the uncoated surface, lot of weight loss, even 10% weight loss in 28 days. But the coated surface is able to control the weight loss. Okay, and we can see the in vitro biomineralization, as you can see from the scanning electron pictures. Then we have to see the cell viability, because ultimately you're looking at how the cells proliferate and grow without getting toxic. We looked at MG63 cells. These are bone cells which are generally used. Okay, so you can see the right hand side is some of the fluorescent pictures. The left hand side is the data in quantitative data. The cell viability is almost 100% with all these material. Okay, day 28 you can see the hydroxyapatite, higher the hydroxyapatite, higher is the cell viability, obvious, because HA is found in the bone. So you can see that. You can see these green and the blue ones. Okay, so increased cell viability. Okay, normal shape. You can see the shape of the cells Mg63. Increased adhesion and spreading. You can see that they are increased cell viability and very good ALP activity, alkaline phosphatase, because alkaline phosphatase tells you the mineralization of the cells. Ultimately, when the bone cells starts mineralizing, that means they are growing well. So the coated surfaces, you can see very high mineralization after 28 days. Initially, they are almost same, but higher the HA, higher is the mineralization, as you can see in this graph. These are collagen deposition. So as the mineralization takes place, collagen gets deposited. After all, collagen is part of the bone matrix. Okay? And so you need to understand how the collagen gets deposited with different coated surfaces, with different hydroxyapatite coated surfaces. And the pictures here shows with the different dyes, and the bar graph show the quantitative data of the mineralization. So you can see with the good mineralization that's taking place, good collagen deposition also taking place with the coated surfaces actually. So the in vitro studies shows that the hydroxyapatite coated magnesium surfaces, collagen gets deposited, the alkaline phosphatase activity is also very good, the mineralization is also extremely high. So the next question is looking at those genes which are involved in the inflammation and mineralization. So we'll look at various osteogenic genes. The ALP is the alkaline phosphatase genes, BMP2, bone morphogenic genes, then collagen type 1, then osteocalcin, then runt-related transcription factors. So all these are genes which are involved in the bone growth. Okay, so we were monitoring these gene growth after 7 days and after 28 days in different surfaces. This uncoated surface, then just a polycaprolactone alone coated surface, polycaprolactone with 10%, 20%, 30% hydroxyapatite, and as expected, the 30% hydroxyapatite coating shows the very highest gene, alkaline phosphatase, highest bone morphogenic, collagen type 1. Okay, we can see. So the key osteogenic gene expressions of these key osteogenic genes are extremely good as expected as we keep increasing the hydroxyapatite level in the protein. So, all the in vitro studies are extremely encouraging. We see that the alkaline phosphatase, the mineralization are very good. The genes that are involved also show very good improvement. So we wanted to go into animal studies. So we did the studies on rabbit. Mouse is too small to create a corresponding defect. We have to go for bigger animal. So we went to rabbit, and this shows a pictorial. So we had two groups of rabbits. One is uncoated, A is at 31, that is your aluminum, zinc, magnesium alloy. The other one is polycaprolactone hydroxyapatite coated same alloy. So the experiments were done on rabbit. So a defect was created on rabbit. And then the material defect in the bone was created, and these cages were placed. So this is a typical picture, as you can see here. You can see our cage here. Yeah, you can see the cage here that's being placed inside. Okay. This is the cage, as you can see in all these pictures, and then they were structured, and so the experiments were done for 8 weeks on rabbits. So we have two groups. The uncoated magnesium alloy was placed in rabbits for 8 weeks and then removed, and then the coated surfaces, aluminum, zinc, magnesium was placed, removed after 8 weeks, and then we looked at how the bone defect which was created artificially grew, what's the bone density, and what are the key genes involved, and how they all came out with respect to these two different materials. Okay, this was done on, as I said, in vivo rabbit. So we did the X-ray studies and the micro CT studies, and then bone mineral density, and in vivo degradation of this particular material as well. So this is the radiography analysis. This is the uncoated cage. So you can see the defect here, and the material is placed inside this day 1, and then the bone starts slowly growing. Okay, as you can see, still the defect is there after 8 weeks. So here, this is our coated and the AZ31 coated cage. The defect is getting filled up very fast. As you can see, practically, and there is no defect. The bone has fully grown within 8 weeks when compared to the uncoated. Here we see the repair of bone defect within 8 weeks is happening from the radiography. Then we perform something called the micro CT analysis. The micro CT gives you an idea about the bone volume, percentage bone volume, as a function of time, and also the porosity. So this helps us to determine whether coated surface and uncoated surface, how they perform with respect to each other. So we can look at the bone mineral density. So this picture tells you how the bone mineral density, it gives you artificial colors just to see how the density. So you can see uncoated surface, okay, then you can see coated surface. Completely healed, actually. The complete defect is filled up. The bone has completely grown. Whereas this is uncoated, you can still see a lot of gaps here. So you can see, again, the coated surface, this is the uncoated surface. So we can compare the bone volume from this picture and this picture. Uncoated after 8 weeks is only 77 millimeter cube. Okay, that's the bone volume. And here we have 143 millimeter cube. Okay, almost twice. A percentage bone volume, again, you can see there. And then thickness, trabecular thickness is higher. Total porosity also is improved. So the polycaprolactone hydroxyapatite coated magnesium alloy is able to create a lot of new bone and good porous bone. Okay. In vivo degradation, we take the sample out and then weigh it. We know the original weight, and then we look at the modified weight. We want to reduce the weight loss because we want the material to stay in until the bone gets completely healed, actually. So we looked at that. So the uncoated material, the degradation in 8 weeks is 40%, whereas with the coated, it's only 5%. Okay, so again, the coating has helped. So coating has helped in increasing the bone volume, percentage bone volume, healing in 8 weeks. It has improved the porosity. At the same time, it's reduced the degradation of the magnesium cage, because magnesium cage is the main which keeps the load in action in main. And okay, when compared to the uncoated surface, we see a lot of improvement in the polymer coated surface, actually. So higher bone mineral density, higher bone volume, as well as percentage bone volume. So we did some histopathology studies as well, and then trying to look at the native bone, newly formed bone, osteoblast, all these related to the inflammatory occurs. So we see that Newly formed bone, quite a lot of newly formed bone is present with modified and magnesium, the surface modified magnesium, which is placed inside the body. As you can see here, NB is the newly formed bone, so we see a lot of newly formed bone with respect to native bone. Okay, this is called a hemotoxylin and assay. Then we do again look at the blood vessels, okay, using some other type of assay. Again, we see collagen formation. Ultimately, collagen is very, very important in the bone. So collagen formation needs to be looked at, and also new blood vessels needs to be looked at. So we do see, as you can see, NV is there, quite a lot of NV is there, C is there, collagen. So the collagen matrix also starts growing. Newly formed blood vessels is also present in the coated is at 31. Okay, so we do see when there is a lot of newly formed bone as well as newly formed blood vessels, and we see collagen deposition also. All these seem to be happening on the newly formed bone, especially with that which is coated with the AZ31 mesh cage. We also see the genes which are also involved, especially the same genes, the alkaline phosphatase. We see similar picture as we saw in our in vitro studies, that the coated surfaces, especially the polycaprolactone and hydroxyapatite coated surfaces, enhances the important genes which are involved in the bone formation as well as which are involved in the anti-inflammatory process. So the alkaline phosphatase gene, the bone morphogenic protein gene, the collagen type 1 gene, all these get enhanced in the presence of the coated surface when compared to the uncoated surface. So we see a similar picture as we saw in the in vitro studies. So the in vivo studies are extremely encouraging with respect to the formation of the bones, especially the bone percentage, volume, the porosity of the bone, the growth of the bone, and the healing process of the animal, and as well as the biodegradation of the polymer, sorry, the biodegradation of the material, which was much lower when compared to that of the uncoated material, because we do not want the material to biodegrade much faster than the material, and much faster than the healing process of the bone defect. So as the bone defect is completely healed and the bone is totally grown, we want the material to get degraded, which may be taking place in about 1.5 to 2 years. So we want a material which degrades at that point of time rather than at the earlier time. So in order to achieve that, we try to design new surface coating material which are biocompatible, and which prevents the biomineralization or biodegradation of the magnesium. Okay, so we are able to achieve that quite reasonably well. So we found many interesting studies from our magnesium-based alloy here. Okay. Titanium is very widely used because of its strength, because it's easy to fabricate and so on. But the problems with, as I had mentioned, with titanium is it leads to stress shielding. It leads to bacterial adhesion because titanium encourages bacterial adhesion, and it is not biodegradable. So we started looking at magnesium-based alloys. There is some interest nowadays on magnesium-based alloys, recent papers, as you can see. But the main problem is how to reduce its biodegradation or bioresorption. Okay, and also It produces gases when it is present in the body fluids. How to reduce that? So these are some issues that are being looked at as of now. In addition to looking at other alloys, which will keep reducing their mechanical properties, mechanical strength, bring them closer to that of the bone. Although that's still not achieved, as I showed you with stainless steel and titanium with respect to the bones, the numbers are vastly different. So we need to have materials which have properties closer to that of the bone, at the same time slowly bioresorb, and magnesium is the best candidate which has been so far found actually. So but the problem with magnesium is the bioresorption is much higher, so we need to reduce that. And I think one of the approaches which I showed you can help you to modify these bioresorption. So by having different levels of coating, or by having different thicknesses of coating, we may be able to achieve much reduced biodegradation as to tailor our requirement, whether it's 1 year biodegradation required or 2 years biodegradation is required actually. So in that respect, we created some surfaces, but these surfaces are highly bioresorbable, so we modified with the polycaprolactone hydroxyapatite surfaces. In vitro studies show very good promising results. So when we went into in vivo also with rabbit studies, we were able to show that the bone volume increases, the percentage bone also increases, porosity increases, some of the key osteogenic genes also increases with time, and the bone growth is as desired, is growing very well, and so which is very, very promising as such. Okay, so let me thank some of our collaborators, especially this study, the surgery on rabbits were performed by Professor Gopalan, Department of Orthopedics, CMC Vellore. So without his support, we could not have performed. And Dr. Govind Raj, who is a research scholar, and various agencies, funding agencies and support agencies who had helped us to carry out these analytical studies, which is widely done here. And as you can see, there is a lot of mechanical, chemical, and biochemical analysis which were done in this study, and lot of support from various agencies as well as with the medical fraternity. And as I mentioned in the previous talk, a collaboration without a medical person, especially in the area of prosthesis and biomaterials, will not take you very far. You may be able to do in vitro studies, and beyond that, if you want to pursue, you definitely require support from the medical fraternity to take your project to higher levels. Thank you very much for your time, and let me thank the organizers for giving me an opportunity to talk to you. Thank you.
Thank you, sir.
If there are any questions, I'll be pleased to answer those.
Okay. Thank you, sir. You addressed the problems associated with polymers, especially the hard facts like mechanical properties, etc., of different materials. So overall, it was a very informative talk on biomaterials and prosthetics. In fact, we were very lucky to have a DOIN, you as a speaker, who has a vast experience in the research on biomaterials. And the case studies were very interesting. And I hope the researchers had good insights into the pros and cons of the biomaterials. So do you have any questions? Okay, I would like to ask you, sir, what will be the opportunity for, say, postgraduate students to carry out internships in your lab or in some other labs associated with biomaterials?
Yeah, internship opportunities are there. Like I mentioned, surface modification. We do a lot of surface modification Like I mentioned, depending upon the location in the body, depending upon the duration, we can do different surface modifications to prevent biofilm, to improve the biocompatibility. So we do a lot of biochemical modification. So opportunities are there. Short-term internship, you can't do too many experiments, but surface modifications we could do, and then some properties could be studied. But if you want to go beyond biochemistry, other properties, then it will take much longer time. But as of 2020, I think internship opportunities are very difficult. As you know, the main reason, nobody is allowed per se from outside to do any research as of now. But 2021, yes, there could be opportunities. But for doing a project of this nature, which I showed you, may will take about a couple of years, if you are including animal studies also. But if you don't include, if you are talking about only in vitro studies, at least a year is needed. Because this requires a lot of expertise, not only on biochemistry, some polymer chemistry, then cell culture work, going right up to PCR, looking at the genes. So 1 year. So if you're talking about a 3-month work, 3 months based internship, or 2 months, one can look at surface modification, look at some properties like contact angle, some mechanical properties. Surface modification could be electrospinning type of modification, maybe a dip coating type of modification, or spin coating. Then look at some antibacterial properties using antibiotic coated surface. So one could do in 3 months these type of activities.
Thanks for sharing that information. Now, for the participants, we are going to have one of your demonstration on surface modification. So thank you very much.
One my question.
Yeah.
Test in chat box. Please see.
Pardon, sir, not clear. Chat box, okay. The question is, one of the final MTech student in machine designing and robotics. So is there any scope in this field? One of
yes,
the students is in MTech final year doing machine designing and robotics. Is there any scope in this field?
I think new material designs is really very important in the area of biomaterials. So as I said, I think biomaterial really grew because of discovery of new materials in the area of space and robotics, which came into biomaterials, like materials, shape-based materials, and then materials which are related to sensors, material. So all these come from research from mechanical engineering and machine design only. I think, sensor-based studies, remote sensing, all these come from that area. And design of new materials with different novel properties, I think they all come from mechanical engineering knowledge only. It doesn't come from a biomaterial scientist at all. Because a biomaterial scientist makes use of new materials, but he or she doesn't design a new material. So I think there is a lot of scope.
Yes. I hope that answers.
How to apply in this field, sir? How to apply in this field? Which organization in India?
Which organization means if you are talking about studies, there are master's courses are there, right? Master's course in biological engineering, master degree course in biomaterials. So there are a lot of MTech based courses are there. So you may have to go into MTech based courses. If you're talking about PhD research, then nowadays in any department, like even engineering design department, mechanical engineering, everybody is working on some sort of a biomimetic type of material, right? Biomimetic material. So you find professors or faculty in different departments of mechanical or machine design, or even engineering design who work on biomimetic surfaces, biomimetic designs, and then write to him or her and try to find PhD opportunities. Because practically everybody in any department has now working on some area of biology or biomaterials or biomimetic surfaces or biosensors. They all come from non-biology background only, right? Biosensors and biomimetics, all the new design, new materials, they all come from non-biology background. So you need to find a place depending upon whether you are interested in MTech or interested in PhD.
Yes, sir, you said it right. So thank you
Okay,
for
thank you,
being
ma'am.
with us, sir.
Thank you, sir.
So we are going to share your demo on surface
Okay.
modification. Thank
Okay.
you very much.
Thank you very much.
This experiment is about
Class is over, ma'am. Class is over.
Of a polymer.
Class is
Polymer
over,
which
ma'am.
we are going to work on is polyester. Polyester is used as a large diameter vascular grafts. It's used in valves, so many other biomedical applications. In order to prevent bacterial attachment and biofilm formation, you can coat this polyester with the antibacterial agents, antibiotics. Here I am going to talk about whether we can coat a material called curcumin, which is a natural product as well as which is used in food and flavoring applications. As you know, curcumin is a product of turmeric, and turmeric is widely used in Indian food industries. It's got anti-inflammatory, antibacterial, even anti-cancer properties. So by coating this polyester surface with that, we will be able to prevent bacterial attachment as well as biofilm formation. We can't directly coat curcumin onto the polymer, so we use polyvinyl alcohol. This is a FDA approved polymer. This is of molecular weight 140 kilodalton. Okay. So we have to prepare a PVA solution in water. So what we do is we take 500 milligrams of PVA in 2 ml water. We heat it to 70 degrees centigrade in a water bath for 15 minutes so that the PVA completely dissolves in that. We take 200 milligrams of curcumin. Curcumin is not water soluble, so we need to dissolve it in ethanol. So we add 1 ml of ethanol. Now we need to mix it thoroughly using a water bath sonication. Curcumin has to be dissolved and dispersed in ethanol, so we use a water bath sonicator. Now we mix this curcumin in ethanol to PVA, which we have dissolved in water together, and then again we need to mix them thoroughly in the water bath sonicator. This is the curcumin completely dispersed in PVA solution. We are going to use this for coating the polyester film. This is called a dip coater. We can coat polymer surfaces using this dip coater. We place the polymer film here and we set the program here, and the solution is placed here. The polymer film goes down, dips into the solution, and the coating is achieved. We can dip it several times. We can dip it once, twice, many times depending upon the thickness of the coating design. Here is where we set the program for the dip coating. I already have a program, it's called program 2. Yeah. It gives the dip speed, millimeter per minute. It gives the lifting speed, millimeter per minute. It is giving the length of the film, that is how long the film is. It gives how long the dipping has to be in minutes. It gives you how long the drying has to take place in minutes, and then how many times you want to repeat. So here I have given 2 cycles, so we can do it 3 cycles, 4 cycles, many cycles. You need to place the film at the tip. This is the polyester film. So you place the film here. Curcumin solution. The curcumin solution is placed below, and we start the run. Now we can remove our sample. This is a curcumin coated polyester with the PVA as the binder. This experiment is a demonstration of coating a surface using a spin coater. Previous experiment we talked about a dip coating, where the sample moves into a solution containing whatever material needs to be coated. Here the sample will be rotating at very high RPM, and when we drop the solution containing our coating material like antibacterial or antibiotic, it uniformly spreads on the surface because your sample polymer is rotating at very high velocity. Okay. So this is the setup here. We are going to use polyvinyl pyrrolidone as a material with the curcumin. As I said, curcumin has antibacterial, anti-inflammatory, even anti-cancer activity. Curcumin is found quite a lot in turmeric, which is widely used as a flavoring food agent in many Southeast Asian countries, especially India. It is reported to have antibacterial activity, so we are going to work on that. Polyvinyl pyrrolidone is used as a drug delivery material and for drug encapsulation. I take this polyvinyl pyrrolidone, that is PVP, 1 gram of it, okay, just got a molecular weight of 40,000 in 10 ml ethanol. And then we mix it thoroughly, okay, for about 5 minutes. We use a vortex mixer for mixing this thoroughly. We take 5 milligrams of curcumin and we add 1 ml of ethanol to it. As you know, curcumin is not soluble in water. And once more we mix them. We add this curcumin solution to the PVP. And again we mix them using this vortex mixer. Now the solution is ready. We can coat it on polyester. As I said before, polyester is widely used for large diameter vascular grafts, diaphragm valves and so on. So polyester is fixed to glass slide using a tape, and it is placed inside the spin coater here. This spin coater also has a vacuum arrangement so that the solvent that's coming out will be sucked out. Now we load the program. As you can see, it will be rotating at 1000 RPM, acceleration in 10 seconds, and then contact time is 100 seconds. We press 1 here and then we say run. Press 1. I take this solution and add slowly, drop by drop. And as you can see, it gets uniformly distributed along the polymer surface. It forms a monolayer. Once the coating has been done, we switch off the program, stop the program, we can remove the glass slide. As you can see, curcumin and PVP mixed material has been well coated on this polyester, and now we can peel out this polymer from the glass slide. This is the polymer polyester coated with the PVP and curcumin. So this will have antibacterial activity, so we can use this for preventing biofilm formation on polyester surfaces.
ഞാൻ കൊടുക്കാം. നീ 15 അല്ലേ? ദീപ ഇപ്പോഴേ പ്രസന്റിംഗ് എന്ന് പറഞ്ഞ് വരുന്നുണ്ട്.
Hello, if class is over, then feedback form is shared, sir. Feedback form shared, sir.
The next session will be starting at 3:15 p.m. The last session of the day will be starting at 3:15 p.m.
3:15 p.m. Okay.
Welcome to CADMark World. CAD-Mark Software, an ISO-certified organization incorporated in 1999, is a specialist engineering company with 15 crores revenue serving 700 customers with energetic certified team. Our mission and vision statement clearly emphasize by providing latest engineering software technologies to customers to build disruptive solutions for betterment of human life by being good stewards of the resources. With 20 years of rich experience, we implement software solutions along with our core services of CAD consulting, professional software training and 3D printing services. CAD-Mark has emerged as one of the most promising engineering company in India and ready to deliver quality services to our clients. Let's have a look at solutions. CAD-Mark partnered with global leaders to sell, support and service their solutions to drive customer innovation. We represent Autodesk for drafting and design software like AutoCAD, Inventor and Revit. As a Dassault Systems Platinum partner, we address areas of product design, styling, systems engineering, PLM solutions and realistic simulation. Accelerate performance and increase design productivity in 3D environment, thorough 2D and 3D mouse from 3D connection. Wide range of 3D printing solutions from MakerBot, a Stratasys company using fused deposition modeling. Finally, ExtraCAD, a product developed by CAD-Mark, help in inspection report automation and ballooning software for AutoCAD and Inventor quickly and accurately. Our esteemed customers are our guiding force. Their valuable feedback helped us to make measurable improvements in our service. CAD-Mark, India's first partner to sell 3D experience platform of Dassault Systems to VSSE for various successful space missions. Dassault Systems solutions are deployed in Cochin Shipyard for ship design activities while helping convert an analysis of defense equipments. We serve India Kawasaki Motors for their exclusive design of racing bikes in Pune. On the other hand, Hyundai Transys excels in seating and transmission. The world-class audio systems and cockpit design is created by Hyundai Mobis. Taking small steps in life sciences industry, Nymans uses Simulia for deep brain simulation. Forest Healthcare do 3D printing of eye testing machines, while Aster Metis Pro manufacture quality life-saving medical devices. Finally, our nation's pride academic institutions, universities, startup missions, government training centers create next-generation leaders, entrepreneurs and inventors. Our motto is to drive customer delight and grow with our esteemed customers. CAD-Mark is happy to serve customers if provided with an opportunity. Come and explore our CAD-Mark world.
United NDT is a pioneer institution which provides oil and gas, mechanical and MEP courses to mechanical engineering students who want to get placed in top mechanical engineering core companies. We are an institution which is 10 years old and approximately 5,000 students have graduated from here, out of which 4,500 students have been placed in top engineering companies. The courses we do are expert in oil and gas engineering with TUV Ringland certification, diploma in oil and gas engineering, mechanical QA/QC, MEP, HVAC and other international certifications like CSWIP 3.1, NIBOSH, AWS Certified Welding Inspector course, BGAS, NECE, etc. The certifications we provide for these courses are TUV Rail in German certification, ASNT Level 2 certification which is internationally accepted, STET Council certificate and NACTET which is approved by Government of India, and in-house certifications which are also valid worldwide, as we are an ISO 9001-2015 certified institution. Our faculty includes IIM graduates who take classes in project management, as well as pioneers in mechanical engineering field who have worked for companies like Saudi Aramco for 20 plus years. Our extensive lab facility is one of its kind and is revered by even our competitors. We guarantee 100% placement with feedback guarantee if you are not placed. For most of our courses and for the remaining courses, we provide placement assistance. Join us for a fruitful career and career advancement in mechanical engineering.
United NDT Training and Inspection Center, Palarivattam, Cochin.
BIRDS, Bioinstruments Research and Development Society, a forum for medical and engineering professionals to interact, identify tasks and solve scientific problems of mutual interest.
Is a part of the Rajagiri Vidyapeetham, a dream eternal being unfolded in time through the relentless CMI quest for excellence in the pursuit of wisdom.
Making the transition from school to college was especially difficult for me because I came from a different syllabus to most of the students here, but the faculty was really instrumental in easing the path. I think in other colleges, professors can be a little more aloof and they don't interact much with students beyond the actual lectures, but that's really not the case in Rajagiri. Our professors are really invested in our education and you really feel supported every step of the way.
An individual's personality defines his character. It is therefore required to nurture and mold it with the right formula in the right manner so as to make a person competent to face the challenges of the corporate world.
Right behind me, what I see is green and luscious area. You can see that all around Rajagiri, the greenery and also its different varieties of flowers. That's the first thing which struck me when I entered this college. Classrooms are equipped with very well designed
Good evening all. We begin the fourth session of day 3. Today we have a researcher in the area of polymer science as our speaker. And she is Dr. Deepa K. Baby, Assistant Professor at Rajagiri School of Engineering and Technology. She had her master's degree in chemistry from St. Joseph's College, Calicut University, and a PhD in the area amphilic star block copolymers from Calicut University. She has more than 8 international publications in the area of polymer chemistry. Her research interests include biopolymers, smart polymers, biomedical applications, and polymer synthesis. With that, I welcome Dr. Deepa K. Baby. Over to you, Deepa.
Thank you, Lisa ma'am. Good afternoon all. Today in this session, I'd like to discuss some aspects about biopolymers and biomedical application. The summary of my talk includes introduction, classification of biopolymers, that is polynucleotide, polypeptide, and the method used for preparing this biomaterial, electrospinning, hydrogels, synthetic biopolymer, biodegradability test, polysaccharides, and among it, chitosan as a drug delivery carrier, then future challenges and references. In the introduction part, we will define what is a biopolymer. Biopolymers are polymeric compounds and it is found in living organisms such as animals, plants, bacteria, and algae. They are polymeric biomolecules. The importance of biopolymers lies in its properties, and the properties are biodegradability. It is having a high degree of biodegradation. Then it is biocompatible and it mimics chemical structures in nature, and also it is having low toxicity, and it also releases non-toxic fragments during degradation. And other properties are, it is easy to process, then it is have high strength, and it is also flexible. Then why this biopolymer is used in biomedical application? First, it is used in controlled drug delivery carriers. In it, controlled drug delivery can be achieved. Second, it can be used in implantable materials. If biopolymers are used in implantable materials, then no need for a secondary surgery is required. That means it will degrade after fulfilling its function. Then it is used as a scaffold, and scaffold is a material, and that using this material you can develop new functional tissues, and it can be used in medical purposes. Then coming to classification, biopolymers are generally classified into two types. One is natural biopolymers, another one is synthetic biopolymers. In natural biopolymers, you have three types. One is polynucleotide, second one is protein or polypeptide, and third one is polysaccharide. Coming to synthetic biopolymers, you have non-degradable and degradable polymers, and in biomedical application, you are using degradable polymers at a larger scale. Then first we can see what is a polynucleotide. Polynucleotide composed of 13 or more nucleotide monomers, and it is covalently linked. And in a nucleotide, you can see a phosphate group, a sugar molecule, and a nitrogenous base. Examples for this DNA polynucleotides are DNA and RNA. Then how it is acting as a biomaterial? The main property of nucleotide is that it can undergo self-assembly. By self-assembly, it can form macromolecules, and it is in the size range 50 nanometer. So different structures can be obtained from this DNA self-assembly. And after that, you can load drug into the DNA structure by different methods, either by covalent linkage or by non-covalent linkage or by intercalation. Intercalation means you can add drug into the strands of DNA, or by encapsulation. Encapsulation means you can fill the drug molecule inside the polymeric structure. Next is polypeptide. Polypeptide or protein, mainly it comes from three sources. One is animal protein, second one is milk protein, and third one is plant protein. In biomedical application, mostly used one is collagen, gelatin, and keratin. And it can be used as fibers, 3D printing scaffolds, interconnected scaffolds, then as a drug carrier, and also as hydrogel. Then how these fibers are obtained from this polypeptide? We are using a technique that is known as electrospinning. The last session, Sir has discussed spin coating and dip coating. This is also another method to prepare a biomaterial, that is electrospinning. In electrospinning, first you have to take the polymeric solution in the syringe, and at the nozzle of the syringe, you are applying a high voltage. And due to this high voltage, the droplets coming out from the nozzle is having a charge. And this charge of the droplet will counteract the surface tension of the droplets, and as a result, the droplet will undergo stretching. And when it moves through the nozzle, then in air, it will undergo drying, and fibers are formed, and it is collected at the collector point. It is also having the charge. And this is the picture of the fibers obtained by electrospinning. And the peculiarity of the fibers are that it is having very thinner diameter, and it is having a large surface area. Then this spun fibers can be used as scaffolds. In wound dressing, it is better because it will prevent the microbial infection, and also it can be used as a sutures and also as drug carrier. For acting as a drug carrier, first you have to add drug into the polymeric solution before it is injected. Okay, so we have a polymeric solution plus drug, and at the nozzle, the polymer is filled with drug and it is coming out, and it can be inserted inside the fiber. Next protein is keratin. Keratin, it is commonly seen in human hair, then horns, feathers of animals, etc. Okay? And it mainly consists of 65 to 96% of proteins, and some other compounds are also there. So this is the cross-sectional view of a hair, and in it you can see cuticle, medulla, and cortex. So in cortex you have microfibril, and inside the microfibril, you can see the microfibril, and inside it you can see the protein. And it is a double helix, 2 alpha helix combined to give the keratin molecule. Then you have to extract the keratin from human hair. And the extraction process is like this. First you have to delipidization you have to do. That means this human hair contains disulfide linkages and it is insoluble in most compounds. So first you have to solubilize this protein in a solution, and you are using a reduction method, sodium sulfide reagent. I am not discussing the chemistry behind it. Then by solubilizing in a buffer solution, you can dissolve protein in it. Then by a dialysis, you can remove the small molecular structure from protein. A purification method, you are using this dialysis. Then you are freeze drying. That means you have to remove the liquid to get the protein. So you are doing the freeze drying. During the freeze drying, what you are doing is you are applying pressure and reducing the temperature. Then sublimation reaction will take place and liquid will be removed. Then what are the applications of hair keratin biomedical field? That means it can be used as a scaffold, then it can be used as a film or matrix for this drug delivery, then as a hydrogel it can be used. Then what are the applications means? First, it can be used as a nerve conduit filler. Nerve conduit filler means it is used for peripheral nerve repair. Okay, this keratin will act as a barrier between this inflamed part and the regenerated tissue. Then wound dressing also it can be used. Then hemostat you can use. Hemostat means it can prevent blood bleeding. Okay, these are the biomedical applications of hair keratin. Then we comes to collagen and gelatin. Collagen, you all know that it is found in skin and also tendons, ligaments, cornea, etc. And it can be isolated from various animals, including the bovine, that is cow family. And also there are different types of collagens. And mainly it consists of amino acids, and the structure is very complex. And the gelatin means it is obtained from collagen. That means if collagen is hydrolyzed, that means you are cutting the peptide bond into smaller peptides. Then you are getting this gelatin. Then this is the structure. The collagen is a triple helix structure. And you are getting collagen fiber that is found in the animal skin. These are the biomaterial available from collagen. First, it can be used as hydrogel, and mainly in corneal implantation it can be used. Then it can be used as a collagenated mesh, then matrices, and also you can prepare hybrid material from this collagen. Hybrid material means you can incorporate either inorganic polymers or inorganic materials or polymers, other polymers in this collagen matrix. Then you can use it as fibers, tubes, etc. Then what is hydrogel? Mainly it is used in corneal implantation. Hydrogels are mostly all hydrogels are hydrophilic, and it can store large amount of water or any biological fluid. And this is due to the chemical cross-link present in it. Either it can be prepared from homopolymers or from copolymers. And due to the thermodynamic compatibility with water, it can swell in water or in biological media. Then you can obtain these hydrogels from natural biopolymers such as chitosan, collagen, dextran, etc., or from synthetic polymers. Then if you are using hydrogel as a drug release, then you can use this equation for finding out the release of drug from the hydrogel, where MT by M alpha equal to K into T raised to N, where MT is the amount of drug released and M alpha is the total drug content in the hydrogel, and MT by M alpha is known as the fractional release. K is the kinetic constant and N is the release component and depends upon the mechanism of drug release that we will see later. And this is the picture of the collagen, which is acting as a drug delivery. You can incorporate drug into the matrix either covalently or by any physical means. Okay, then when it is taken to a physiological condition or in intestine or in blood, then it will undergo desorption and also diffusion to release the drug into the medium. The next is collagen-based scaffolds. So we have discussed what is a scaffold. It is used to generate tissue from the cells. For that, first we can use a collagen matrix. It contains so many pores, and into the pores you can add the mesenchymal cells, stem cells, that is taken from bone marrow. Stem cells taken from bone marrow is known as mesenchymal stem cells, and you are adding growth factors into it for the nutrients. Then the cell will grow and proliferate, and you will get different tissues, cells and tissues from this scaffold. Next we can discuss synthetic biopolymer. Mainly synthetic biopolymer most commonly used one is polylactic acid, polyglycolic acid and polycaprolactone. All these have similar properties. Polylactic acid belongs to alpha hydroxy acid family, and it is found in plants such as corn, potatoes, etc. And also it can be synthesized in lab also. Then it is heat resistant up to a temperature of 110 degrees Celsius, and since it is very hard, it can be used in medical implants. And depending upon the type of usage, it will degrade within the body. It has lifespan of 6 to 2 years, and gradually it will undergo degradation. So it acts as a supporting carrier for the bonds. Next is polyglycolic acid. Mainly it is known as absorbable sutures. Mainly sutures are made from this polyglycolic acid, and it is developed since 1962 and under the trade name of Defect. And the degradation product is glycolic acid, which is a non-toxic. And also glycolic acid can be eliminated through urine also. Then polycaprolactone, it is a semi-crystalline polymer, and it is also the peculiarity of polycaprolactone is that it is soluble in most solvents, and also it can be used. Enzymes and fungi can easily biodegrade this polycaprolactone, and it is mainly used in correcting facial aging, and also it is used in drug delivery also. Then next we can see the proteins obtained from microorganisms, that is polyhydroxyalkanine. It is polyester, and it is known as bioplastic. So bioplastic means it can be degraded using microorganisms. So this comes to green economy. And again, it is used in orthopedic applications. Then how this biodegradability test is done for this biopolymers? Mainly depends upon different factors. First one, depending upon the microorganism, then also the physical and chemical conditions of the polymer, the biodegradability depends. And the mechanism is that when you are adding a biodegradable polymer, the enzymes and microorganisms will act upon it, and you are getting CO2, H2 and some other fragments. And humidity, temperature, pH, all other factors governing this biodegradability. This is done in an incubator chamber, and it is carried out at a temperature 60 degrees Celsius. And you have to humidify the incubator and also pass oxygen in it. Then it will undergo degradation, and the fragments and the carbon dioxide evolved is calculated. This is the biodegradation curve obtained. First, we can see a slow increase in slow biodegradation, and after that, there will be an active biodegradation point, and it reaches at a plateau region, and at D, it comes to an end. Next is polysaccharide. Polysaccharides are generally monomeric sugars, and it is linked by glycosidic linkage. Examples are starch, cellulose, chitin, chitosan, etc. Starch is found in plants, and also you have cellulose. And most important polysaccharide used in biomedical application is chitosan. And chitosan is obtained from chitin, which is found in the exoskeleton of prawns, crabs, etc. It is semi-crystalline, and you can see the structure of chitosan. It contains so many hydroxyl groups. As a result, it is hydrophilic, and therefore it is insoluble, highly hydrophilic, and therefore it is insoluble in water and all common organic solvents. and it is having antimicrobial property also. But the drawback of this chitosan is that it is insoluble. So we have to modify chitosan for increasing its solubility. For that, we have to modify this chitosan with other polymers. So I am discussing how chitosan is acting as a drug delivery carrier. So generally, a polymer is used as a matrix or membrane for drug delivery. You have to achieve some properties. First, they have to be biocompatible, and also you have to load the drug in a strong way. A strong bond should be there between the polymer and the drug. Then these are the systems by which drug delivery is done in the form of micellar, in the form of vesicles and nanospheres, nanocapsules. Likewise, you can use this systems as drug delivery. Then the drug release mechanism depends on three main reactions. One is disorganization, second one is diffusion, and third one is degradation. Disorganization means when it is taken into a medium, the structure will reorganize. Okay, reorganize and form another structure, and thereby drug is released. Second one is diffusion. That when physical bonds are there, and by diffusion, release of drug will take place. Then by degradation. So when it is taken to understand the pH, acidic pH, the polymer itself undergo degradation. As a result, the crosslinks will be degraded and drug will be released. So for a drug carrier, the polymer should be biocompatible. Next property, it should be cost effective. Then it should have a size range between 10 to 200 nanometers. So easily rapid renal filtration and elimination will take place. Then the polymer drug bond should be strong enough, and during storage and transportation, no drug should be lost. Then we have to, I am discussing with chitosan, so we have to modify chitosan for increasing the solubility. For that, we can see what is amphiphilic copolymers. Amphiphilic copolymers means it is having a double affinity, that is to hydrophobic and to hydrophilic environment. And as a result of this self-assembly, they can organize into different architectures. Mr. Lace vesicles are some example, and this can be used as drug delivery systems. So, chitosan or micellar, when it is used as a drug carrier, the main reason is that micellars are very easy to keep. Second, it can dissolve sparingly soluble salt in a better way. Then there will be less toxicity for this micellars. Then there are two methods to modify this chitosan. One is grafting from, another one is grafting on. In grafting from method, first chitosan is taken as a backbone, and to which you are adding small molecules. Thereby, another polymer is made on the backbone. That is grafting from. Second process is grafting onto. Grafting onto means you have the same chitosan backbone. You are taking another polymer and using a functional group, you are attaching this polymer to the backbone. That is grafting onto. Generally, chitosan can be modified with these derivatives. Steroid derivatives can be used, fatty acid, aryl and alkyl, and carboxymethyl derivatives of chitosan can be used. Here I am using NIPAM as a polymer, and it is incorporated into the chitosan polymer. First, I have incorporated Lilial. Lilial is a drug, and that is mainly used in cosmetics, and structure I am not discussing it. First, you have to incorporate Lilial into chitosan as by a chemical reaction, and it is a covalent bond and it is very strong. Then this chitosan Lilial is combined with NIPAM. Why I am choosing NIPAM? Because NIPAM is thermoresponsive. Thermoresponsive means between a temperature swing of 25 to 32 degrees Celsius, this NIPAM can change from hydrophilic to hydrophobic. Below temperature or below 25 degrees Celsius temperature, it is hydrophilic, and above 25 degrees Celsius, it is hydrophobic. We all know that our body temperature is 37. So, this NIPAM is acting as a hydrophobic moiety at this temperature, 37. So that is why I had chosen NIPAM. And this is the term image of NIPAM chitosan linear nanocarriers. You can see this term image at different pH, not at different pH, it is at different temperature. One is at 25 degrees Celsius, another one is at 37 degrees Celsius. In the first A, you can see the micellase are in larger size. That is due to the reason that NIPAM is hydrophilic. So pH 7, it is in a swelling manner, therefore size will be bigger. When it is taken to a higher temperature, that is at 37 degrees Celsius, NIPAM becomes hydrophobic. As a result, the size of NIPAM shrink or it becomes hydrophobic, and therefore the size gets diminished. That is seen in the figure B. And this is the term image of the same micelle at pH 4.5 at 37 degrees Celsius. You can see the diminution of size in a large extent. That is, when it is taken to pH 4 and at temperature 37, the size gets diminished at a greater extent. So this is the point where we can use it as a drug carrier. So this is the linear release profile at two different stages. The red line shows the linear release at pH 7. Okay, pH 7, there is no release of drug. Then when it is taken to pH 4, then the size decreases. As a result, the drug inside or trapped inside the micelle is taken out. As a result, you can see a release of lineal from the micelle. And the mechanism of this is explained like this. This is the micelle. At lower temperature, the red lines are NIPAM, and inside you have chitosan, and the yellow region is the lineal drug. So lineal is trapped inside the micelle and it is at a safer place. At temperature 25 degrees Celsius. When it is taken to higher temperature, that is above 25 degrees Celsius, then reverse process takes place. That means now NIPAM is hydrophobic. It will be inside the micelle and chitosan will be outside. So since chitosan is outside, lineal is there with the chitosan and release of drug takes place. Another example is amphiphilic polystyrene chitosan copolymer. This is also amphiphilic. Polystyrene, it is hydrophobic and chitosan is hydrophilic, and it is also undergo self-assembly. And you are getting, and this is the reaction, how it is prepared. I'm not discussing it. And the characterization techniques we have used is NMR spectroscopy. You are getting both chitosan and polystyrene incorporated. Then GPC will give the molecular weight of the compound. Some analysis also shows the that means chitosan is incorporated in this polystyrene. Then this compound can be used as for the generation of nanometals. Nanometals can be generated from this chitosan polystyrene copolymer. And this, when chitosan polystyrene incorporated with nanoparticles, then chitosan itself is having antimicrobial property. So if you are using metal nanoparticles in it, the property can be enhanced. So it is a very good method for or very good material for wound dressing. And this is how it undergoes self-assembly, and how this nanoparticle is formed in this chitosan polystyrene copolymer is like this. We are getting, by self-assembly, this polystyrene chitosan will form in micelle. And I told you earlier that chitosan contains hydroxyl groups and NH2 groups. Then the metal, when it is added in bulk, it will react with this NH2 and OH groups and form a bond with chitosan. And after that, since micelle formation, this metal is entrapped inside the micelle, and as a result, separation of particle takes place. And this is how you are getting nanoparticles in the micelle, that is chitosan polystyrene micelle, you are getting nanoparticles. This is the term images of the nanoparticles. you can see nanoparticles embedded in the micelle, and the nanoparticle size is of 20 nanometer. And this is mainly due to a mechanism that is coordination reduction mechanism. I'm not discussing it, this coordination reduction mechanism. And this is the proof for the metal nanoparticles. Then same matrix, inside to it you can attach quantum dots. The quantum dots cannot be attached to all polymer matrix. Some specifications could be needed. So I have docked this cadmium selenium ZNS quantum dots into this chitosan graft polystyrene matrix. This is the image shown of quantum dots, and this, if quantum dots are incorporated in the polystyrene chitosan matrix, then it can be used for targeted drug development. So these are the applications of chitosan for drug delivery, and that's how, and with this slide I am coming to an end of the session. These are the references I have chosen, and the future challenges of this is that you have to understand the intracellular and extracellular modulators of cell function, and also novel materials and techniques which is more biocompatible with the biological interfaces have to be found out. Better strategies for immune acceptance, that is another challenge, and also you have to replicate complex tissue architecture. Okay, and I am acknowledging Director of Rajagiri School of Engineering and Technology, Principal RSUT, colleagues, and also the organizers of FDP for giving me such a wonderful opportunity to present. Thanks once again for your patience. Thank you.
Thank you, Dr. Deepa. That was a detailed talk on biopolymers and its applications. You have introduced us to a variety of biopolymers and the method of developing them. Thank you once again for your time.
Thank you.
So with that, we conclude. Okay, thank you.
Thank you.